All right, guys. So now we move on to the next part of the lesson. So in the previous section, we covered all the 2D objects, right? So we were finding center of mass for completely 2D objects. And now we actually move on to the 3D section. And this is more important because you will mostly be tested on 3D, on the 3D section, because 2D was something you learned in M2 as well. So now we are going to go into rigid bodies, right? Okay, so uniform bodies basically. Okay, so when it comes to the uniform bodies, okay, so you can see they are giving you certain criteria. The weight is evenly distributed through the body. So obviously the weight is going to be evenly distributed. So in this case, in uniform bodies, you will most of the time be working with volume, right, guys? Because you are working with 3D objects, so your weight is going to be distributed through the volume. And the center of mass will lie on any axis of symmetry. So this is of course a thing that we always use, right? So whenever there is an axis of symmetry, center of mass is surely going to be on that line of symmetry. So that's going to definitely help you to, reduce finding, if you're finding to a single coordinate, because when there's a line of symmetry, definitely you will be directly able to find one coordinate using that. And they say the center of mass will lie on any plane of symmetry. The center of mass will lie on any plane. So guys, when it comes to 3D objects, you know there are planes, right? Not just line, but plane. So basically, when there's a plane of symmetry, the center of mass is surely lying on the plane of symmetry. All right, guys. So the first body that we learn under this is the uniform solid sphere. So this is actually a really easy one, right? So when it's a sphere, the center of mass of a uniform solid sphere is at the center of the sphere. That's quite obvious, right? So if it's a sphere, the center of mass of a sphere is surely going to be in the center of the sphere. This point is the intersection of the infinite number of planes of symmetry and is the only point which lies on all of them. Guys, do you understand that there are infinite planes of symmetry here? Now, you know, plane is not a line. So basically, in this case, we can consider the planes as, so can you see I'm drawing plane here inside this. So this is another plane. Can you see inside this plane, circular plane, also the center of mass is, the center of that is over here. Can you see I can draw many different planes here? Guys, can you see? So in all, because all the planes that you draw here, symmetrical planes are all going to be circles. Right, guys? I hope you are getting what's going on here. So basically, all you need to know here is in a uniform solid sphere, the center of mass is exactly in the middle of the sphere, right, guys? So that's quite a simple one. So let's move on to more complicated, to more, difficult objects now. All right, guys. So the next shape is a uniform solid right circular cylinder. So this is also quite an obvious shape. So you really don't need to go through a lot of trouble to find the center of mass, right? Right, guys? Because you can see the center of mass of a uniform solid right circular cylinder is at the center of the cylinder. So it's really obvious. Why? Um, because in this kind of a shape, you can see that you have the center of, you can see there is a symmetrical plane, right? Can you see there's a symmetrical plane in the middle and there's another symmetrical line that goes exactly. So you have two planes of symmetry meeting each other. So definitely where the planes, when the planes of symmetry meet, it's surely the place where they meet is going to be the center of mass, right, guys? So that's really obvious. So in a cylinder, the center of mass is at the center of mass of a solid right circular cylinder is at the center of the cylinder, right, guys? So remember, it's a solid means the inside is filled. By the way, the inside is not empty, right? Even in the hemisphere, a solid shape means inside is completely filled with that same material, right? So these are some obvious shapes. So we'll now move on to the more difficult shapes, right? So guys, look at this. In P4, I think you have learned something called where you find where you create objects by using the technique of solid of revolution, right, guys? Do you recall this that theory? So where they give you a curve and you rotate that curve 2 pi radians around the x-axis and you create a 3D object, volume of revolution. Yeah. Okay, so you you create a solid by revolving the curve around the x-axis, and you create a complete 3D object by using by using that technique. And then in P4 you have learned how to find the volume of that particular object, right, guys? So that was something you learned in people. So now the next part here is we are going to actually what? You can see here. So this y equal fx, you can see I have highlighted on top here. This is your original curve. Are you guys with me? So this is what was originally given to you. All right, guys. So this is 0 and this is the place where the curve is ending. What you basically do here is you take this curve and you rotate it 360 degree around the x-axis. And then by rotating, you create a complete 3D object. So, you know, when you're rotating, what you should do is you should create an exact same replica uh, below the x-axis, right? Whatever you have on top, just create. And then every open end becomes a circle, right? That's how the open end becomes circle over here because it's a pointed end and meeting, you don't get a circle, but the open end becomes a circle, right, guys? So so what we're going to do now is in M3, what we're going to do here is we are actually going to learn how to find the center of mass, of an object that you create through this revolution, solids of revolution technique. Okay, so we are going to learn how to find the center of mass. One thing though is really important. You know that when you do a solid of revolution, definitely the center of mass is going to be what? So when you do a solid of revolution, if you are revolving around the x-axis, the center of the x-axis is going to be a line of symmetry. Right, guys? The x-axis is going to be a line of symmetry, which means what? Definitely your center of mass is going to be on the line of symmetry. So for any solid of revolution, if it's revolving around the x-axis, the y bar is going to be 0, surely, for all the objects, right? So the y bar is going to be 0, only the x bar is going to be the problem. So you'll have to find x bar. All right, guys, so you'll have to find x bar. Okay, so you can see here what they're saying. So to find the solid of revolution, this time when you're breaking the strips, guys, actually you can see the way, can you see the way they've broken the strip? It's delta x, and you can see the strip is not just a it's not just a rectangle now, because you can see the strip is going all the way to the other side. So you basically have like a disc. Can you see? So it's not just a rectangle because it's not a 2D object. Now it's a 3D object. So basically you have like a small disc, a small cylinder, right? So the width is delta x. Okay, so fortunately for you, the proof of that is not required. You are directly actually given the formula. Can you see? You're directly given the formula. You're allowed to use this formula. Okay, you are directly allowed to use the formula. So we'll directly go into that. So they say here for a uniform solid of revolution, where the revolution is about the x-axis. The center of mass lies on the x-axis and its position on the x-axis is given by the formula x bar equals integration of y square x dx divided by y square dx. Can you guys see? I think this proof is actually not that. I think you can go through this stuff on your own. You can kind of like understand what's going on here, right? So and they've built up this equation. So basically all you need to know is how to use this equation. Using this particular equation, you are going to generate the equation or the x bar for all sorts of 3D objects. Okay, so guys, this is not actually that bad. I think you can go through this part. So mainly what I want to focus is on this equation. Okay, so you are directly allowed to use the equation. So that's why I'm directly going into this. So guys, over here, x bar is integration of y square x dx over y square dx. Or they have given another formula for you. Capital M x bar equals rho pi y square x dx. Okay, so what's going on here? Okay, so what's going on here? So so basically what's happening here is, guys, you need to understand capital M here is the mass of the solid object, and rho is the density. All right, guys. So basically, if you are completely going with integration, you can use this formula. But if you are going with, how do you say, if you know the object and if you know the volume, right now I told you the mass is going to be proportional to the volume. Right, guys? So if you are going to go with the volume, if you know the complete volume of this particular object, you can go with the second equation. Right. So for example, in this particular shape, if you take this particular shape, I think you can see it's not something that we know the volume. Do you know? I mean, you don't know how to find the volume of an object like this, right? So in, in a case like this, where you do not know the complete volume of the object, it's best you go with the first equation. X bar equals integration of y square x with respect to x divided by y square with respect to x. So go with this equation because you don't know the total volume. But if it's an object that you know the total volume, maybe like a corn, so we'll go into those parts soon. So we'll actually see how to apply these equations, right, guys? So don't worry. At this point, just write it down, and I'll show you exactly how to apply the equation. Okay, so that's really important. The application of these equations are so important. I'll explain. I'll demonstrate that to you via examples. Okay, and then just to note down, they say always they also give you another equation for a uniform solid of revolution where the revolution is about the y-axis, right? So sometimes the revolution, and up here the revolution is happening around the x, but they can also do a revolution around y, right? So you can do a revolution around the y-axis. So if you have an object like this, if you revolve around y, you get something like this, right? So if you do a revolution around the y-axis, so they say they have given you the formula to use for that point as well. Then if you're revolving around the y-axis, I think you understand that x bar is definitely 0 because you're on the y-axis. So you only have to find y bar, right, guys? So the equation for y bar is integration of x square y dy over x square dy, or if you know the total volume, you can use my bar equals integration of rho pi x square y dy, where m is the known mass, rho is the density. So guys, both of these equations are really important. If you know, once again, if you know the total volume, it's easier to use the second version. If you know the total volume, it's easier to use the second version. Okay. If you don't know the total volume, then use the first version. Okay. So then these are the two versions. So now what we'll see how to actually apply them. Okay. Over here, one more thing, when you are revolving around the x-axis, y bar will be 0. Okay. So these are the things you need to know. So make a note of this and we'll go for some application. Okay, guys, so you are also requesting me to explain how this part comes as well, right? So it's actually quite easy how they've taken the proof here. Okay, so just to give you a small heads up, so they say here now I told you that we are dividing this into strips, but each strip is becoming a disk, right? So each disk has a width of delta x, and you can see this is actually a tiny cylinder, right? So and the center of mass of each disk is exactly in the middle. Do you see? So the if this particular, so we mark this as x. The center of mass of, so you take one disk, we are focusing on one disk, and you can see the center of mass is quite easy, right? So over here what you do is you get the mass of a disk. Okay, so mass of a disk is going to be what? So it's the you have to take the volume of the disk. So it's actually a cylinder. So what's the volume of a cylinder? Pi r square h, right? Pi r square h. So pi, and what about the r? So guys, the radius here is the y length. Can you guys see? It's the y length here. Can you guys see? The radius of the disk is the y length here. Pi y square, and the pi r square into height. So what is the height of the disk, guys? The height of the cylinder is the width, is thickness here, right? So the height is delta x. Can you guys see? So I'm just doing it to show you guys, okay? Because how the equation comes, it comes together really easily. So then the mass of the disk, you have to, you get the volume. Okay, so volume you multiply with rho. Rho is the mass per unit volume. Okay, so rho is the mass per unit volume. So pi y square delta x into rho, right guys? Is that clear? So pi y square delta x is the volume of the cylinder, the tiny disk, and multiply by rho, and that gives you the mass. Okay, and then what about the center of mass of the disk? Center of mass of disk. So is it difficult? Do you have any complications now? No, it's directly x, right? Center of mass of the disk is directly x. It's directly x. Okay, and then so let's apply the equation. Sigma mi(xi) equals total mass into x bar. Right, guys? So sigma mi(xi). So what's the total? What's the mass? Pi y square delta x into rho, and the x coordinate is x. Total mass. Now, in this case, you can see for the total mass, I don't know the total volume. I don't know the total volume. So I will take the mass of a disk and take the summation. Okay. So we will go in the traditional way because we do not know the total volume. So pi y square delta x into rho and then x bar. Right, guys? Okay, and then you know what we should do here. As delta x goes to 0, the summation becomes integrals. And so you have here integration pi y square x times rho delta x becomes dx. Right, guys? And over here integration pi y square rho and then delta x becomes dx. X bar is a constant. Okay, x bar is a constant. Right, guys. So you can take the constants out of the integral sign. So pi is a constant, rho is a constant, and you have here y square x with dx equals here pi is a constant, rho is a constant, and you have inside y square dx, and then x bar. X bar is anyway out of the integral sign. Remember, x bar is not inside the integration at all, right? As I told you, x bar is a constant for the shape that stays out. Pi and rho cancel. Can you guys see? So pi and rho cancel, and you have your x bar equation. It comes together really easily. Y square x dx over y square dx. Guys, can you see how it comes? So basically your integration, by the way, I did not put the limit. So your integration limits are going to be, in this case, we are doing with respect to x. So the values start, x values start at 0 and they end at a, right? Can you see the limit they have used here 0 to a? So basically whatever the limit you have, okay? So basically use the limits according to the shape. So I'm not, I mean, you can't just focus on this question, like, in general questions, the limits depend on where the curve starts and where it ends, okay? So you need to apply the limits accordingly. So I will name here AB because it won't become always 0. Don't expect it to always be 0. So I'll just use here A and B. Okay, so because in this case our A value is 0. In this example, A is 0. Okay, okay, they have already used A here, right? Okay, that might confuse you, right? So just give two. I mean, in this situation, the limits are 0 to A. All right, guys. But but when it comes to different solids, the limits might change. So you have to do it accordingly. Can you see that we got this equation? Okay, and then basically the other equation they got here is when the volume is known, right, guys? So just to show you, if the volume is known, if total volume is known, right? If total volume is known, then in that case, then total mass is known. Then total mass is the total volume, right? So total mass M is equal to, I mean, you multiply the volume with the rho. Are you guys with me? So you multiply the volume with the rho value, and that's how you get the total mass. Are you with me? That's how you get the total mass. So basically, when you're using that equation, it's the same thing, sigma mi xi equals the sigma mi. Can you see the total mass? Okay, so this is the total mass is sigma mi here. The total mass is going to be, we are using capital M here. Are you guys with me? The total mass is capital M here. Right, guys? So the right side part is going to look exactly the same, and you'll end up getting this, right? Yeah, so now you have the pi and rho. So you end up getting this. I mean, the right side part, all of these parts, sigma mi xi, all of these are gonna come, and you'll end up getting here pi y square x rho dx equal total mass into x bar. Guys, can you see this is exactly the same equation that we have? Let me arrange pi and rho y square x dx. If you pi and rho can come out of the integration sign, that's fine. Pi rho y square x dx. Can you see this is the second equation that they have given? Can you see? Capital Mxy equals pi into rho into y square. So this is the second equation. Is this clear, guys? This is how the equation has been formed. It's really straightforward and it's really easy. Okay, so you guys wanted me to explain that. That's why I showed you how the equation came. So around the y-axis, really, I really don't want to, take time on that. So that's quite easy. In that case, your disk will be forming in this manner. So your disk will be delta y now. You see, so this is how the circular disk, the cylinder comes. So this is delta y. and the coordinate, you can use the radius. It's the exact same precision, you can get the answer, right guys? So this is just to show you, because you wanted me to show how the equation works, how it was created. I just showed you how they have used the theory and how they generated both of these equations. Okay, all right guys, it's I hope it's clear now. So let's go for some application.